Thank you very much. And I'm happy to show you a little bit the possibilities of track reconstruction algorithms for non-HEP applications. And therefore, I would like to first motivate why it is interesting to map particle and to airplane track reconstruction algorithms. What are the aims of track reconstructions with airplanes? What are the similarities? What are the differences? Before I will come to the recent project, the quantum graph neural network approach, where we'll just show you the edge network and the node network before we'll summarize. So the motivations that algorithms pave their way from science into society is, in case of the airplanes, there are similarities because they are dedicated flight paths, but the main difference is that in particle physics, of course, you would like to have collisions, and the aviation industry would like to avoid these collisions. Both, let's say, industries expect a huge amount of data. In physics, the Halloumi LHC run, and in the aviation industry, the data coming from air traffic as the recording of the data via satellites is now officially launched, and so you can broadcast more data. You can have in both cases an object identification. In case of the airplanes, it's possible to identify each unique airplane via their unique transponder. And in particle physics, as you all know, you can identify the particles that came through the detector. And last, it's an interesting R&D study topic, and we do this with GluonNet Testis in collaboration with CERN Open Lab, Caltech, MET, Ankara, DAISY, and CERN. And we would like to explore the use of the novel techniques such as quantum computing, and therefore for the physics applications I would like to refer you to Cheng Tuji's contribution, which I linked in the presentation if you're interested later on. So the aim of the track reconstruction with airplanes is, on one hand, the improvement of flight safety, so that you can better predict emergency situations and give some recommendations how to avoid them. Another case is that you can use it for an incident tracking. Furthermore, you can use it, the track reconstruction, for anomaly detection, which means detection of every unusual behavior based on the flight plans, which can be due to crisis regions or regions affected by weather. So, because then your flight path will deviate. Furthermore, you can address environmental aspects, which are getting more and more relevant, so that you can recommend the best possible flight plan according to the data and reduce the amount of the carbon footprint. And from the economical side, you can this helps you to improve cost and efficiency, which means that you can reduce the fuel consumption of the airplane if you have access to the best possible flight path. You can improve the airport capacity, yes, and you can deal better with the expected huge amount of data. So, for example, just to give an illustrative example, you can see the flight paths over the world in April 2019, recorded during 1 hour. So you can see here, for example, or here, these distinctive patterns. And before we'll come to the R&D study, I would like to highlight you a little bit of the similarities. So when we speak in particle physics of a detector hit, the analogy would be in the aviation industry or with the airplanes, the timestamp with the position. The event ID in particle physics corresponds to the ID of the airplane transponder, which is unique, whereas the particle ID corresponds to the airplane type. For example, if there's an A380 or a Boeing 737. As I will speak in the following of graph neural networks, I would like to introduce you to two additional words, which means the edge. It would be the closest distance of approach in particle physics, and the airplane language in quotation marks, it is the distance between two airplanes, and the node is considered as airplane. So this brings me to the introduction, and we did this work, or it's ongoing work, with the CERN Open Lab, Caltech, MIT, DESI collaboration. And as I mentioned before, the physics applications you can find in Chengdu's talk, and the archive link is the refers to the proceedings that have been published in relation to the HEP. So this quantum neural network based on the HEP-Trax approach, in which the HEP-Trax collaboration uses in quotation marks, the classical graph neural net. And it was the idea to study if it's possible to apply this in terms of particle track reconstruction using quantum computing techniques, as there's a huge amount of data expected during the high luminosity run of the LHC. And in addition to that, we have been curious to apply this algorithm outside of HEP, and at the moment we are integrate the flight data on it, but other applications to other areas of society are possible as well. And basically this quantum graph neural net consists of a classical input network followed by a quantum edge network and a quantum node network. What this is, I will explain on the next few slides. And both quantum edge net and node net are applied iteratively to deliver the best result. So in case of the airplanes, you assign the qubits to one airplane, and the airplane of interest is surrounded by these neighbor airplanes. And one quantum circuit is applied for each possible neighbor, and then you need another set of qubits for the recurrent iterations. After the measurement, you will get the node information. So we use this together to get a good understanding of the risks for the collisions. And I would like to mention in addition that here you can see as a bold line the detector hit, or the timestamp that that is broadcasted in addition, and the coordinates of the airplane are transmitted as well. In case of the edge neural network, you integrate the node features, which are marked here. And in addition to that, you apply additional qubits to get the so-called hidden features. And on a classical level, this would correspond to hidden layers in your neural network. When you take the measurement, you get the edge information that gives you the most likeliest connections between two airplanes. And for example, this is some other work we did with preprocessed data from April 2019, and which I'm sorry. So in the left plot, we reconstructed the airplanes and highlighted them which are closer than 57 kilometers. It has this number has something to do with a collision alert system. So this marks basically the factor of 3 of this collision warning system. Before this will raise an alert, but just to have it a prior warning that there might be a collision during the next 20 seconds. So these are the timescales in which we usually think. And another study we did for the airplane track reconstruction, you can see it here in the data with the underlying world map, and here in a 3D plot. And the overall goal for our motivation to apply this quantum graph neural network is that we have learn some risky combination of the flight patterns with the help of this quantum graph neural network. And this brings me to my summary, that the airplane track reconstruction are triggering similarity to particle track reconstructions, but of course they are not. They have similarities, but they are not the same. And there's a variety of needs in aviation industry, as I mentioned, that can be addressed using this type of neural networks, but they are not limited to aviation and aviation industry as well. And then I showed you the quantum graph neural network, so the present status of the non-HEP application side, so that we gather a good understanding of risks for collisions, and the training with the flight data is ongoing. And as last step, I would like to thank all of the contributors who made this possible, and especially Daniel Dorbos, who allowed me to present the talk. And yes, then I would like to thank you for your attention, and if you have some questions, please let me know.
Thank you, Kristiane. Questions for Kristiane? I want actually, so I've seen similar presentation for the use of quantum computer for tracking. The question I have is that in the case of airplane trajectory, is there I don't have a good feeling of the resource needed in terms of compute power to do this. I mean, you want to turn to a quantum computer if you think this will bring a significant improvement in terms of resources, eventually when they are available, of course.
So it depends a bit on the view, because for the aviation industry, you deal on average with the existing broadcasting submission, which includes not very much information. You expect 500 gigabytes roughly per month, which is almost nothing compared to particle physics. And for the airplanes, it's at the moment so far so good with the classical computing techniques, but as one of you know, there are drones coming up, which have to be taken into account as well, and so this might be a possibility to incorporate them and to deal with them as well.
Okay, thanks for that. Any other questions? Okay, so then this concludes this morning or afternoon session, depending where you sit. And so we will resume at 7 p.m. European time, and as we will not risk to give another time zone would be wrong, afraid to be wrong. And Maurice Garcia-Silvares will be sharing this second session of today. So thanks a lot.